multiple choice, but a little bit longer. So same as final exam is same format as the hour exam, but it's a lot longer. And it's scheduled for 2 hours, but because it's at nighttime, we can kind of stay until the custodians kick us out. Okay, so there's kind of no time limit, generally speaking. Usually, when I'm trying to close it down, there's maybe 5 to 10 people left, and I'm saying, okay, last 5 minutes. Okay, so for the vast majority of you, it will be a no time limit exam. Okay, yes, sir.
What's the arrival time for the final exam?
Just be there by 7. Make sure you're there before, just a little bit before 7. I'll get, like I said, I'll get you the room number and an announcement, and I'll post the final exam study resources, which is mainly a sheet. So the final exam emphasizes exams 2 and 3, and then the material that we do this week is heavily emphasized. Okay, so what we do today is not directly on exam 3. There may be some things involved with the topics that we covered, but today's stuff is not directly on exam 3, but very important for the final. Okay, all this week, we're going to return back to the big picture of calculus, and it's all important stuff for the final exam. Other? Yeah, please.
So that means optimization and related rates are on test 3 and on the final.
Yeah.
So if you're having trouble with those, then we have office hours today and tomorrow, normal office hours for you guys to get help for test 3. For the final exam, we're going to have special review sessions since final exam week is weird, we're not doing normal office hours for final exam week. So instead, we're going to have a couple study sessions, which Mark will post eventually on Blackboard.
One on Monday, one on Tuesday, right?
Yes, we're going to have one on Monday from 9 to noon, and then we'll have another one on Tuesday morning from 9 to noon. So we're hoping that one of those 2 becomes,
okay.
You can drop in for part of the time, you don't have to be there the whole time. Yeah.
So is there also a review session for exam 3 or just?
Yeah, just for the final exam. So for exam 3, you have normal office hours that you can go to. So there's office hours today and tomorrow throughout the day. You can get help. Anna first email is always available. And then for final exam, we're having the special review sessions since we don't have office hours last week.
Yep. So normal office hours today and tomorrow. My office hours are tomorrow from 11 to 12:30. I can stay a little bit longer than that also if you just give me a little heads up. And so I know to wait for you. But so my office hours middle of the day, but then all the TAs have their normal office hours. And then, yeah, 9 to noon Monday, 9 to noon Tuesday, drop-in study session. We won't have anything prepared, but we will be there to answer your questions and facilitate you guys studying together, okay? So you want to study as much as you can over the weekend. That will maximize your benefit in those study sessions, right? Don't show up to start studying in the study session. I mean, it's better than nothing, but the best thing to do is get going over the weekend so you can bring your questions and dialogue with other students, having some foundation of readiness, okay? Any questions? Okay, so we want to return to the big picture of calculus. Most of the semester, we were on a specific journey, okay, and to a destination. And so some of the things were kind of offshoots, very important. For instance, optimization, related rates, really important topics, but kind of more a little bit offshoots off the main road of this big picture and this destination we're heading for. So let's just do a quick recap. In the first half of the course, we looked at the situation. You know how fast something is changing at every moment, and you want to know how much of it you have at every moment. How do we know how fast something is changing at every moment? How would we know that? A rate of change function, right? A rate of change function tells us how fast something is changing at every moment. And then we want to know how much of it we have at every moment. What's that? Accumulation. So either a net accumulation, meaning the amount of change from a starting point, or total accumulation, which would include however much you had when you started, okay? So either net accumulation or total accumulation would be what we mean by you know how much of it you have. Okay, so here's an example. So this example is On the left, we have exact rate of change of elevation. So as a function of distance from the border. So this is the rate of change of elevation as a function of distance from the border. And then over here is a function E, which is elevation change from the border. Okay, so this is how much the elevation has changed from the border. Okay, so is that total or net accumulation? Is that total? If it's how much the elevation has changed from the border, is that total or net? That's net accumulation, right? How much change we have, right? Because, you know, at the border, we could be 1,000 feet above sea level, but this is marking how much change we have from the border. So that would be 0 at the border, okay? So using, task for you, using the exact rate of change function R, so in terms of R, write a function capital F that gives the exact accumulation of elevation starting from C miles to X miles from the border. So now I'm going to come along here and say I'm C miles from the border, and now I want to write a function F that gives the accumulation of elevation starting from C miles to any amount X miles from the border. Can you write a function F like that? Can you write a function F like that? Because the accumulation of, in terms of R. So you can write a function in terms of R that gives the accumulation of elevation starting from C miles to the border until any value X miles from the border. Okay, so seeing if we learned it, seeing if we learned this before. Super important question. Can you write this function capital F? Capital F. Try by yourself. If you can't get it, maybe get a hint. This is E, right? So this is change of elevation from the border. Now we're talking about a function starting from C miles from the border to X miles from the border. So the question is, what is F of X? Okay, compare. So if you think you got it, compare with the person next to you. Or get help. If you didn't get it, get help. Capital F function. In terms of R, the net accumulation of elevation starting from C to X miles from the border. Okay, so I'm just curious, how many people think or know they have it? Think or know they were able to do it? Oh, you're breaking my heart. In terms of a rate function, how do I write accumulation function given a rate function? How do I do it in general? One person's got it. Okay, good. Yeah, so hopefully at least you thought integral. All right, integral is given a rate function. Given a rate function, we can write a accumulation function. In this case, net accumulation starting from C miles from the border. So that will be just what he said. Okay. So this is the change in elevation starting C miles from the border as a function of X miles from the border. Okay, is this an open form or a closed form expression? And remember what an open form is. Open form reflects a process, right? It reflects a process, but doesn't generate the quick results that a closed form does, right? So it reflects a process. What process does it reflect? So the integral sign means what? Sum, right? Accumulation is a sum, right? And that's an S, right? That's a German S standing for sum. Okay, summing up what? Summing up rates? Are we summing up rates? No, that doesn't make sense. Summing up rates doesn't make sense. What are we summing up? Bits of accumulation that we find by constant rate of change, right? M delta X, right? That's going back to the first week, right? So we're gonna take bits of change, each one we get by our math of constant rate of change. Delta Y equals M delta X. And so that's right there, right? M delta X is the same. Really the idea of R of T dt. But now our changes are super small, right? Our changes are super small. Okay. Hopefully at least ringing bells. But this is super important stuff. I mean, this is what calculus. So this what we're talking about is bringing together so many things we worked on all semester. Okay. So and then we said when we got this far, we said how to find a closed form, right? How to find a closed form. One will give us more rapid results of this net accumulation starting at C miles from the border. Okay, so this was kind of the missing piece of the puzzle. And we did work on this a little bit, but let's review it. So starting to talk about closed form means writing the same function f in terms of e. So how could you write the same function f of x using the function e? Which is what? That's telling us change of elevation from the border. So how can we use function e to write f of x in a different way? Go. Everyone work out. Think of it by yourself, and if you need help, then get help. So over here, same thing, using e. All right, just for my own curiosity, how many people think or know they have this one? A few more, okay? So how about back there in the green shirt, what did you say? F of x plus h, so what was that? That was our open form of rate of change of f. Is that what we want here? So that expression that you just told me gives rate of change. So is f of x, capital F of x, rate of change? No, so what about, is it integral of e of t dt? No, because capital E is totally different than rate, right? It's not rate. E is accumulation of height or elevation, but just starting at the border. So how can we use that to write f? Somebody knew. Ian, go ahead.
It's E of x minus E of c.
Right. So if we have if we know the change from the border at x and we know the change from the border at c, then we can take final minus initial to get our change from c to x, right? Okay, so this is starting to get towards now the idea of how are we going to get a closed form, and it has to do with this. Thinking about writing this net accumulation function in two ways. Using the rate, and then using some amount function or another accumulation function, okay? So we can write net accumulation starting at c in these two different ways, using function r first and use function e. Any questions on that? Okay, so then we turned the tables and we got to the point where we were doing the mastery exam. What was the mastery exam? So the mastery exam, these rules enabled us to find what? Closed form rate functions given accumulation functions, right? All those rules we learned were given an accumulation function. What was a closed form rate? So going the other way, we were pretty quickly able to get all these rules for finding closed form rate from closed form accumulation. So this is the key to the missing piece. What we did in the mastery exam is the key to the missing piece of how to get closed form accumulation functions from open form accumulation functions, right? It's just going to be thinking about mastery rules in reverse, right? So if we know how to get these rate functions from accumulation functions, well, now given a rate function, can we think of the mastery rules, but the other way, in reverse, to come up with a closed form accumulation function. All right, but it all starts with this idea right here, this idea that there's two ways to represent net change in a quantity. There's two ways to represent net change in a quantity, using a rate function and an integral, and using final minus initial. Both are expressing the net change of, in this case, the quantity of elevation. So let's talk more about this. So we're talking again about getting closed form accumulation functions from rate. So here's the general, this is what we have, but just in general now. So the integral from a to x of r of f t dt equals f of x minus f of a. Where the r sub f is the rate of change of f, right? Where r sub f is the rate of change of the f function. So again, the accumulation of small changes of a quantity from a to x is equal to the net change in that quantity from a to x. So you can do it bit by bit, or we can kind of look at it as a total net change, but they both give the net change. They both give the net change. Okay, so example. Here's a function, accumulation function, 3x squared minus x. What is the rate of change function? What is its exact rate of change function in closed form? And all masters said 6x minus 1, right? Easy. Okay, so then that tells us something. If we had this open form accumulation function, integral from 4 to x of 16 minus 1, now we know how to write that in closed form. Can you do it? Can you do it? So that's net change. So now we want to express that in a different way as net change. And you can write it, and in doing that, you can write this as a closed form. What's the other way? So think, what's the other way I can write this? Net change, but without an integral. Hint, look at the top. Hint, look at the top. So what would it be? Just use f. So if f is the accumulation function, this is equal to, what do you think? F of x minus f of 4, right? It's going to equal f of x minus f of 4. The net, this is the other way to write that expression, that open form expression, as net change, right? Final minus initial. But we know what f of x is. What is f of x? 3x squared minus x, and we know what f of 4 is. Just plug 4 into that. So we have it, right? We have it. We have a closed form representation of integral 4 to x 16 minus 1 dt. Did you catch it? Does that make sense? Okay, another example. E to the x to the fourth. E to the x to the fourth. What is the rate of change of e to the x to the fourth? Everyone write it down. Okay? What is that? E to the x to the fourth. Did you get it? E to the right. E to the x to the fourth times 4x cubed. And we can throw the 4x cubed in front if we want. Don't have to. Doesn't matter. Okay? So knowing that, here comes a open form accumulation function. So knowing that mastery derivative now allows us to write this open form accumulation function in closed form. Do it. Okay, somebody new. Tell me. No volunteers? Somebody new. Yes, sir. Good start. And what is f of x minus f of negative 1? Right? Got it. Right? So e to the x to the fourth minus e to the negative 1 to the fourth is a closed form representation of that open form accumulation function. Right? So where this reflects the process, this will generate values of net accumulation quickly. Given any value of x, you can just crank out values of net accumulation quickly. Sorry. Any questions on that one? Another example. Okay, what's the rate of change? Did you get it?
I got
4 cosine 4x. Agree with her? Yep, good. So now, find a closed form for this open form rate of change function. Sorry, open form accumulation function. When you're done, check your work. Okay, so but we want to just be careful that we're not just now we're starting to follow a pattern and turning our brain off, right? So make sure we're always asking ourselves the meanings of the things that we're writing down. Okay, so just and we will continue to do that. But again, this is two different ways to write what? Tell the person next to you. So these are two different representations of what in general? Tell the person next to you. Two different representations of what? And be specific, okay? So be specific. Okay, so in general, there are two different forms of what? Net change or net accumulation. And now here's the details starting from pi over 3 when the rate of change is 4 cosine 4t. When the rate of change. So if we're going to start accumulating at pi over 3 with a rate of change of 4 cosine 4t, both of these expressions are going to equal to the net change that you'll get for the net accumulation. One in open form, one in closed form. Okay, so here's another example. So if g of x was the square root of e to the minus x squared, then r of g of x is equal to minus x times the square root of minus x squared. Now that's after some simplification. So that might not look right to you at first glance. But if you're not convinced, work it through. All right, 1 over 2 square root of interior times rate of change of interior. If you simplify all that, this is the easiest, the most simplified form of that. Okay? So take my word for it and do it later if you want. Okay? So here you go. Task for you. Given this rate function, right, it's accumulation function. If the accumulation starts at x equals -2 in two ways, in open form and in closed form. Go. And then compare with people around you. Compare. So make sure you check it out. Okay. Somebody new. Tell me the open form. Open form that I'm looking for. Somebody new. Yes, sir. Mm-hmm. Good. Okay. dt. All done? For the open form? So what about this for open form? Agree? Where do you want me to write R? So this is R of G right here. Is that? Yeah. So you could have written R of G of T here if you want to use function notation. You could have written R of G of T here, but so he just chose to use the rule. So yeah, R of G of T or the rule, they're equal, so both would be valid. Questions on that? Okay. Closed form. A closed form expression. Somebody new. Yes, sir. e to, so like this. Yeah. How do you do? That's it. That's it. Any questions on this one? So we're gonna investigate this one here before I go on. Any questions on that? Yes, please. You good? Okay. That's the best way to answer a question yourself. Figure it out. Other questions? That's not always comfortable, but that's the best way. Here we go. So let's look at that. Here is that. Oops. Why is that black? Okay. So here is that function right there. So we said, the rate is negative x e to the negative x squared. Is that what we said? Is that the rate we had for the original accumulation function of e to the minus x squared? So then I'm graphing that open form accumulation function. Okay? What's the result of starting accumulating at x equals negative 2? So see that there, we're starting at negative 2. What's the upshot of that? What's the result of that? Yeah? At negative 2, it's equal to 0. Why does that make sense? So at x equals negative 2, you see that the value of that function, that integral function is 0. Why does that make sense? Okay, we're starting from, but given the meaning of this function, why does it make sense that at negative 2 it will be 0? Yeah.
It's a net accumulation function. At
Right.
-2, we have an accumulator.
Good. So it's net accumulation is the amount of change starting at negative 2. So at negative 2, how much change do we have? 0, right? So it's a net accumulation. So at negative 2, we have 0 change yet. As x increases from negative 2, then we start accumulating. Okay? All right. So important question here. What will happen to the graph if I change that starting point from negative 2 to negative 1? And don't put this in GC, by the way. We want to think about it. Don't put it in GC and just do it. But what will happen to the graph if a equals negative 1? What will the graph be of y equals negative 1 to x of that same rate function dt? Okay, so take a minute. So what will the resulting graph be if I start accumulating at negative 1 instead of at negative 2? So come up with your thoughts about that. Okay, so I'm sure there was a variety of ideas. Did some of you have this conjecture? So I want to look at one possible conjecture in this case that, come on. Some people have this conjecture that this will be the new graph, at least some. Okay, good. All right. So why does this make? Why would you think this? Why might you think this? Because if it's negative 1 to x now, then we expect what? We would expect it to be 0 at negative 1. Okay, so this is a Conjecture. What does a conjecture mean? It's kind of like, maybe? That's the idea of conjecture. Maybe it's this. And now we want to convince ourselves yes or no. All right, so we're not saying it's true. We're saying this is a possibility to investigate, right? Possibility to investigate. Okay, so in order to investigate that, let's look at what do the two accumulation functions we've looked at have in common? So if you look at this, where am I? So our original one, oh, get the wrong side of the pen, no wonder. So I got the original one here, and now this new one. What do they have in common? What's the central feature that's the same about both of them? Same rate function, okay? Same rate function. So let's come along over here to around 0.5, say at this intersection point. So if this, for whatever x value this is, a little bit less than 0.5, or maybe it is 0.5, I don't know. It's somewhere around 0.5. If our conjecture is correct, then what? At that x value where they intersect, they should have what? Same rate function. And that's true about any x value. So say this one here, where there's a relative max there. Here's another. So call this x1, call this x2. Do we get the same rate of change? So just look at these two examples at x1 and x2. Do we get the same rate of change in both functions? How can you generally characterize the rate of change of our conjectured function here? Positive. For a change in x, y goes up. And what about our original function? Negative rate of change. Certainly cannot be the same. What about here at x2? Rate of change of our conjecture is close to 0. Relative maximum. Rate of change of our original? Negative. How about our conjecture? It doesn't make sense because, yes, it starts at, we got the -1 starting, this is right. But then the rate of change of our conjecture, it's a different rate of change function. It doesn't have the same rate for all values of x. We found 2 examples. All we need is really 1, but if you look at any value of x, we're getting very different rates, okay? Or a rate profile for each of those. So how about our conjecture? No good, right? No good. So we need to start again. So we want to preserve this idea that starting at -1, if it's going to be that accumulation function, that at -1 we want the net accumulation to be 0. But then also our function has to have the same rate profile. So for all values of x, we got to have the same rate as our original net accumulation function. Talk again. Go. Talk again. How can we do it? How can we get both? Okay, so now that we've talked, somebody new. So we want to get rid of this conjecture is no good. By moving it that way, like that, to the right, we get a totally new rate profile. The rates don't match up anymore. So how can I keep the same rate profile for all values of x, but get that starting value at -1? Somebody new? Yes, sir. Shrink inward. Okay, so like, I think I know what you're saying. So something like this. Still like max there, and then like, is that what you mean, kind of? So do you really mean shrink? You said shrink this way. So condense. Yes, sir.
Just shift the whole graph is downward so that it intersects the left tail at -1.
Okay, so he just wants to take the whole graph and move it down so that it goes through -1. So by moving it up and down, do we preserve the rate profile? Yeah. And some of you may have thought of that the first. So did some of you think of that the first time I asked the question? Bravo. So that's really good. So we're going to move it up and down because moving it up and down is going to preserve the rate profile. So I'm going to turn it on, and what will we see? So there's the second function. It's got that starting 0 net accumulation at -1, but for any value of x, we just like kind of draw a vertical line. It's going to have the same rate. Same rate. Okay? So how does that play out then in the closed form? So now take a look here. -1. Look at here's the two closed form versions of the two functions. How do we see that same result, algebraically in those equations? How do we see the exact same thing happening in those equations? The first one is our original, the black. Second one is the blue one. Now these are in closed form. How does the closed form agree with this result here in the graphs? Anybody see it? What did we say? So to get the same rate function with a different starting point, it's just a shift up and down. How is that reflected in those equations? What's that? Subtract. Yeah.
I was thinking the y-intercepts are the second part of each equation.
Yeah.
And that's just we have an mx in front.
Yeah.
And then that's our b, so that reflects the two different.
Well, that would only be if this was, it's not really 0 though. So they're not lines, but you got the right idea. What is this right here? It's a constant, right? It's a constant. And what's this? A different constant. What happens when you change a function by a constant?
You move it up or down.
Right, because this is just playing with the y value of all the points, right? You're just going to change all the y values by the same amount. So because we're just subtracting a different constant is why we get a vertical shift, right? Vertical shift. So just a different y constant on the original part that's the same in terms of x, right? The f of x. Okay, so what happens when we change a? Let's see, where am I graphing that? Here, so just come here and do. So by changing a, so now do you see down here the value of a? By changing the value of a, it just keeps that same rate profile and a 0 net accumulation at a. So notice what can never happen. What can never happen? That function can never do what? It will never drop below completely below the x-axis because you have to have 0 net accumulation at a. If it did that, it would never cross the x-axis. So as I take a from -2 to 0, it moves down, but then when I now start making a positive, it moves back up again. It's not going to go down below the x-axis because you've got to have that 0 net accumulation at the starting point, or an x-intercept, right? An x-intercept. Okay, so huge important thing here. So, given a rate function, how many net accumulation functions are there for that rate function? One? Infinite, right? So given a rate function, that you're looking at it, right? Given a rate function, there's all kinds of net accumulation functions that we could create depending on where we choose that starting value of x. Okay? Given a net accumulation function, how many rate functions does it have? Given a net accumulation function, how many rate functions does it have? Just one. That's like the mastery test, right? So given an accumulation function, it only has, at any given x value, there's only one rate of change at that moment. And that's true for every moment. Okay? So let's return to that conversation. Questions on this discussion? Okay, so what we're really talking about here is the idea of antiderivative. Antiderivative. Suppose f and g are functions. G is called the derivative of f. In other words, g is f's rate of change function. If that's true, then f is an antiderivative of g. Right, so this is the key to writing open form accumulation functions in closed form. Antiderivative. Antiderivative. So here's derivative, mastery test, right? Given a function, write its rate of change in closed form. So now, given an open form accumulation function, to get closed form accumulation, we're going to do antiderivative, right? We're going to think of all the same rules of the derivative, but in reverse, right? We think, oh, now I have a rate of change function. What function, if I perform the mastery rules on it, would give me this function, right? So thinking in reverse. We're not going to come up with a whole new set of rules for antiderivative. We're just going to know the derivative rules really well, so we can backpedal. Okay, every accumulation function is an antiderivative of its rate of change function. And how many accumulation functions are there for rate of change function? Many, right? Many. But, yeah, so yeah, however, every rate of change function has more than one antiderivative, right? Okay, so let's try this. Oh no, we don't do this now. Okay. So I've got this rate function. 3x squared. And so here's an open form accumulation, net accumulation for that rate. 1 to x 3t squared dt. Can you write closed form? Can you write a closed form rate of change function for that open form accumulation? Sorry, closed form accumulations, right? So can you write this accumulation function in closed form? So what's different about this? What's different? We did these before earlier in class. but now there's something that's different. What's different? It's up to you to come up with what? The function whose derivative is 3t squared. Right? So now we have to look at this and think, this is a rate of change. What function has that as its rate of change? Leo, did you get? What's that? So, t cubed? So the closed form of this would be x cubed. Is that right? Equals x cubed. Agree? Yeah, so minus 1 cubed, right? Oops. Guess I didn't have that on there. Okay, so, yeah, so x cubed is going to be the function whose rate of change, or one of the functions whose rate of change is 3x squared. I'm on the other page. Shoot. Try this one. One more try. Try this one. There we go. Okay, so x cubed would be a function whose rate of change is 3x squared. So that qualifies as what? An f of x. So that we could write this as what? X cubed minus 1 cubed. So how can we check to see if that is, what's one check we could do to see if that accumulation function is correct? What could we do? Oh yeah, good, we could put in GC, but algebraically what could we do? Take the derivative of it. What's the derivative? 3x squared. So that's one quick check. Since the derivative is 3x squared, we know that whatever accumulation function we get, its rate of change would have to be 3x squared. Okay? So that's not a complete check. That doesn't check completely, but it is a partial check of that. Okay? So what about this? Negative 2 to x, 3t squared dt. Somebody new, tell me. Closed form of this. Yes, sir. X cubed minus negative 2 cubed. Is the derivative 3x squared? Yes. Okay, here's one. Integral from pi minus 1 to x, 3t squared. Somebody new. How about right here in the black shirt and the glasses? Did you get it? Uh-huh. Is its derivative 3x squared? Yeah, because no matter what constant we have, the derivative of the constant is 0. We said every rate of change function has more than one antiderivative, right? So depending on where you start, depending on what x value you start your net accumulation. Okay, so this brings up this idea of an improper integral. So we've never seen an integral without what's called limits of integration. So so you take those off, and what does it represent? Now it means all antiderivatives of 3x squared. So it's the whole family of antiderivatives for any starting point. For any starting point. So if there's no limits of integration, then what we're saying is any starting point of our net accumulation. And so then we call those, not improper, indefinite, right? Not improper. Sorry, wrong term. That's improper is Calc 2. Indefinite. Got my meanings crossed there. A definite integral is all the ones we've done so far, where you have limits, whether that's a function or not. You have limits of integration, that's a definite integral. Indefinite integral has no limits, and it means starting value could be anything. The starting value could be anything. And so in all those cases, what do we get? We got that it was x cubed minus a cubed, the starting value, right? So any starting value a, x equals a. And then if the starting value is x equals a, in all cases, then basically our antiderivative is x cubed minus a cubed. And we said that minus a cubed is just a vertical shift, right? It's just because it's a constant. So we can also write that as that minus a cubed as just a constant, c. So that minus a cubed, you think we can call that plus c, plus c. So in this case, the constant is the opposite of a cubed, the opposite of the starting value cubed. So this is now in general, an indefinite integral of a rate function dx is, so any antiderivative evaluated at x minus at a, which we know that's just a constant, so we can just simplify that to f of x plus c. So you can think of it this way. What is that constant c? It's the constant required to get the right vertical shift so that what happens, right? It's the constant that we need to get the right vertical shift to ensure what? That at x equals a, we have 0 net accumulation. So that's what that c is about. What vertical shift do we need on that accumulation function so that at x equals a, we get 0 accumulation? Questions on this? Indefinite integrals, right? So indefinite integrals, all antiderivatives. Any starting value x equals a implied, okay? So now we'll do this other thing here. So let's look at, yeah, please. Yeah. Absolutely. Yeah, that's what c is. C is the opposite of f of a. That's what it equals every time. The opposite of f of a is the value we need to get a equal to 0. Sorry, accumulation equal to 0 at x equals a. So yeah, c equals the opposite of f minus a. Good. Okay, here's a rate function. 1 over 1 plus x squared. I want you to represent the accumulation function starting at x equals 1 in open form and in closed form. Represent accumulation function starting at x equals 1 with this rate in open form and in closed form. See if you can do it. else here for open form? Did you get open form?
Yeah.
Tell me.
The integral from 1 to x, and then r of x dt.
So he wants the integral from 1 to x. So I want to use the rule here. Can you use the rule for me instead of the function notation?
Yeah, 1 over 1 plus x
So 1 over 1 plus x squared
squared.
dx. Is that right? Right. Remember what happens if they match? Then at any given value of x, what do we have? We end up with a constant rate. Whatever rate we have at x, we get the constant rate all the way from 1 to x. And so what we want, right, so we need a different variable for x that will get all the different rates from 1 to x, right? So we need something else. So t is fine. I'll just, for to mix it up, I'm going to use u, just so you just don't get in the, it doesn't have to be t. Any other symbol than x, right? So I'll use u. But if you use t, you don't have to change it. T is fine. Agree with that? Open form? Okay. Closed form. Somebody new. So I want the closed form. Closed form net accumulation function that's the same as that one in open form. I know he's got it. Somebody new. Yes, sir. Arctangent of x. So in GC, that's a tan. Okay. Minus a tan, arctangent of 1. Is that what we're going to say? Is that what we're going to say? Yeah. Is that the closed form? Right. What function has as its rate of change 1 over 1 plus x squared? So you remember from the derivative. So we don't learn a whole new set of rules. We just know the mastery rules so well that we can do them in reverse. And that's what we're doing, right? So what should happen when I graph this? If we did it right, I should get the exact same function. And what do we see about that function? So it's the same, right? So purple plus pink, dark pink plus blue makes indigo. And then what else do we see? X equals 1, we get accumulation of 0. So net accumulation is 0. Okay, so up till now we've thought about this as we're starting accumulating at 1. Are we really starting it? So I want to challenge that. Are we really starting accumulating at 1? Why not? So yeah, we got 0 net accumulation at 1, but think about x increasing from left to right. Did we really start accumulating at 1? Why not? Go ahead. Yeah, we got graph over here, right? So we've got points over here, points of accumulation over here to the left. So we might want to rethink this language of starting accumulation at 1. So far, we've always talked about like the lower limit of integration as where we start accumulating. So when she said it's infinite, so really we start accumulating at negative infinity. And so we want to kind of change the way we think about this. Instead of starting at 1, we're starting at negative infinity, and then what happens at 1? What happens to the accumulation? It reset. Well, it doesn't have to go positive. It's 0, right? So yeah, so in this case it goes from negative to positive, but it wouldn't have to necessarily do that. But rather than starting at 1, it's kind of like we get a reset at 1. See that? So we're gonna think about this lower limit of integration not as where we start accumulating, but really where we get a reset of the value of the accumulation. So we're gonna think now we're gonna start accumulating at negative infinity, and this accumulation function will be such that when we get to 1, it'll get reset to 0. And that's more consistent to what we're seeing here. Does it make sense? Okay, another example. And what would happen if I start accumulating at negative 3? So if I go from negative 3 to x, arctan of x minus arctan of negative 3, how would the graph be different? Shift it down. Shift it up. It'll be shifted up. So you get the same profile that goes through what? negative 3. So now that's starting, so that's our reset, right? That's our reset at negative 3 now instead of 1. Okay, one more example. Here's the rate function. 4/3 x to the 1/3 cosine of x to the 4/3. And I want you to represent the accumulation function with a reset at x equals negative 2.5 in open form and closed form. Go. Open form and closed form. Shoot. That's, oh. Hopefully we got open form down by now. Open form should be easy. This closed form, a little more challenging. Goes back to the mastery. So I'm looking at this function, and you got to ask yourself, what function would have this as its derivative, as an answer on the mastery test? What function would have this as an answer on the mastery test? Can you see it? Yes, ma'am. Sine of x to the 4/3. There's one nod over here. So how could you check? So you can make a guess, and how could you check? Take the derivative, right? So you know you can do that. So as long as you can get something close, a guess that's close, take the derivative of it and compare it to what you started with. And then you can see if you got it or not. So she's offering up sine of x to the 4/3. Is the derivative of that the rate function that we started with? Yeah, by the chain rule, right? Cosine of x to the 4/3 times rate of change of the interior. So, if you really know your mastery rules well, you can recognize that. You can recognize, oh, this is chain rule, and it's gonna, that 4/3 t to the 1/3 is gonna kind of collapse back in, right? Going backwards. But again, take a guess, take the derivative, and check it. It works. This works. Is that our closed form of this? Minus sine of negative 2.5 to the 4/3. I hope that's, nope, that didn't work. I think that worked now. So if I graph them both, what should happen? Green plus yellow is trendy. What happened? This might be this.
Because I'm getting the column 2.
Oh, wait. So it should be negative 2.5 and then to the, here, 4/3. what do we see? That it goes through 0 at? Negative 2.5. So this is a quick check right here. Boom. Reset, right? It's not starting accumulating, but we get that reset. Reset of net accumulation of 0 at negative 2.5. Questions on that example? Okay,